with 4 talks, 3 invited and 1 regular. The first talk will be given by Lane Martin. It's about compositionally graded ferroelectric thin films. Please.
Great, thank you. And thank you to the organizers for the opportunity to present this work. And when Peter invited me, he specifically asked that I talk about some of this work on these compositionally graded films. So I'll give you a couple of vignettes in this regard, and I'll try to leave you with one kind of new, interesting observation that we have in these systems. Before we jump into that, let me acknowledge the folks who actually make this work possible. So here's our group back in Berkeley, and I've tried to highlight with some arrows here some of the people who have done things over the years in this regard. So we'll see work from them. We have excellent collaborators at Berkeley and around the country and around the world. And of course, we're always very thankful to those organizations who support our research. Okay, so in our group, we make these thin film versions of these materials, and one of the things that the community in general has been interested in over the last few years is really understanding how you can kind of push the envelope of what you can get from these sorts of materials. And so the question that might guide us here is, how can kind of next generation approaches to growing and controlling and manipulating these materials produce exotic states of matter and phenomena in these ferroic systems? And over the last couple of years, our group has looked at a number of different things, and I'll point out just a few of those here. The first is just simple things like changing the orientation of the material. We saw talks this morning about how growing 1-1-1-oriented versions of things like BFO can drive emergent new phases and structures. And we've seen interesting phenomena related to switching in materials in that regard. We've also looked at the use of strain gradients. We saw talks this morning about flexoelectric effects in materials and what these strain gradients can do, and you can get changes in properties and performance there. And we've even seen stuff, presentations looking at superlattice structures and the types of emergent phenomena that can happen therein. We don't have time to go into all of these things, and as I was instructed, we will focus in on these strain gradients, and I'll give you a couple of examples of the interesting things that happen in these systems. So to motivate this, we don't need much background here, other than to say that if I combine a strain gradient with a polarization, I can have some sort of flexoelectric effect inside of materials. And this has been known for many years. In the bulk, there was lots of great work, and I am surely not referencing all of it here, just some of the highlights. Where this field started was looking at bulk materials and taking these bulk materials and bending them and seeing what can happen. And very quickly, people figured out that you can induce these polarizations. It's a 4th rank tensor. You can get this in pretty much any material. Now, the early work, which focused on these bulk materials, was limited by the fact that they could only apply relatively small strain gradients before the material would break or fail. So this is kind of the units that we're talking about here, kind of on the order of about 0.1 to 1 per meter strain gradients. And that, combined with the relatively small flexoelectric coefficients that most materials have, meant that we knew this existed, but it was kind of a laboratory curiosity in these systems. Now, fast forward a little bit, and people observe some interesting things in thin films that would motivate you to take a closer look at this. And again, I'm highlighting just a few examples here. This is work from Gustav Canalan and company, where they observed that near domain boundaries inside of ferroelectric films, they could have large rotations of polarizations and local strain gradients inside of the materials that give rise to these interesting polarization profiles. And even in systems like this holmium manganite, where you can have oxygen vacancy distributions or inhomogeneous distributions, and they reported strain gradients on the order of 10 to the 5 to 10 to the 6 per meter, so many, many orders of magnitude larger than what you could accomplish in a bulk version of the material. And if you can have a strain gradient this size, well, you can start to do interesting things with it. So what we wanted to try to do was to come up with a way to kind of controllably and repeatably produce these sorts of and magnitudes of strain gradients. And the way we started to do this was by making these compositionally graded versions of these materials to try to bring these two things together. Okay, so I'm going to give you examples in kind of canonical classic systems. And the first system that we'll look at is this barium titanate derived system here, where we're going to alloy in strontium into the system. And so we can pick N members to this process. We have barium titanate here, room temperature ferroelectric phase. We can put 40% strontium into this phase, and we can make it a room temperature paraelectric. I can pull out the kind of pseudocubic lattice parameters for these materials, and I can pick a substrate from our commercially available sources here, and I can start to grow these structures. So here's the kind of relative lattice mismatches, a pretty large compressive strain and almost no strain at the other end of the spectrum. If one does a very simple kind of phenomenological Landau-style model here to look at the polarization as a function of temperature for these materials, we can see that if we grow the parent materials, these two systems here, on this gadolinium scandate substrate, we would expect an enhancement of transition temperature in barium titanate up to, say, 420, 430 C, and we would see that the transition temperature for the barium strontium titanate would be, kind of just below freezing, below room temperature here. So when we go to make these things, we're going to start by making the parent versions, just single layers of these two materials. But then we can also make these graded versions, and we'll have this naming kind of nomenclature here. We'll talk about upgraded films, where the content of barium is going to go up as we go through the thickness of the film. So we're going from this material at the bottom to this material at the top. And then we can make the equivalent downgraded version of this material, where we go from barium titanate at the bottom all the way to the barium strontium titanate at the top. So we'll carry these sorts of things through, and we'll see how they're different between the uniform films and these graded films. All right, so one of the things Peter asked me to do was to give a little background on how we actually make these sorts of things. And so in our group, we do primarily pulse laser deposition. So this is kind of a nice artist's rendition of what's going on inside of this system. We have an excimer laser that comes in. It creates a plasma plume of the material, and we can deposit this down on a substrate. We can control lots of temperatures and pressures and things about this laser material interaction. And all the while, if we really desire, we can watch this using reflection high energy electron diffraction, or READ, to understand the growth process in these materials. So if I show you a map here of the intensity of this specular spot from the READ diffraction pattern as a function of time, you get these kind of characteristic oscillations. So if we're growing in a layer-by-layer fashion, we can grow one layer. Every time you see an oscillation here, we're growing one layer of the material. But if you zoom in and take a closer look, you see that these bigger oscillations have little things that are happening on them. And so if we start counting here, what you're seeing is that each one of these little oscillations is an individual laser pulse, and it takes something on the order of about 16 pulses to make a unit cell of this material here. So in general, we can control these things such that we need about 10 to 20 pulses to grow a single unit cell of these materials. And what that means is each pulse of the laser is sub-unit cell in nature. And so it's possible to do some very intimate mixing of different materials. And so what we do is we put multiple targets in here, and we have a piece of software that helps us coordinate the laser with the target rotator, and we can switch between the different targets of the end members to build up these smooth gradients. So the example of the barium titanate, barium strontium titanate, if we assume something like 20 pulses per unit cell, which is about what we had, we can start with layer 1 here, where we put 20 pulses of barium titanate to every 0 pulses of the other material. If we go to the 5th layer, we're now at 16 and 4. We go to the 10th layer, we're at 11 and 9. We can break this up however we desire to make sure that we get a nice uniform mixing. There'll be, of course, a little bit of diffusion as we go through here. That's probably a few unit cells. And what we end up with at the end is a pretty uniform version of this material, and I'll show you some pictures and data to kind of confirm that. So this is the process that we go through, and we can pretty much mix any end members that you want. And we can even make uniform compositions of the material from 2 different end members if we desire. Okay, so here's the kind of films that we can produce this way. So this is just regular X-ray diffraction data for these different films. If we look across a wide angle of theta to theta here, we see that we have nice, uniform, kind of single-phase epitaxial films. Probably a little more useful is if we zoom in and take a look about the 002 pseudocubic diffraction condition. So we can have a barium titanate film grown on the gadolinium scandate substrate. We can have a barium strontium titanate. This has almost 0 lattice mismatch with the substrate, and so the peak is hiding under the substrate peak here. And if we make degraded versions, what we see is kind of constant X-ray intensity across this range of X-ray diffraction angles in the system, suggesting that we have a continuously varying lattice parameter inside of this system. All right? So we can create these graded versions of these materials. Now, we better make sure that we actually made the graded structure that we suggest. So this is Rutherford backscattering spectrometry data, or RBS. And what you're seeing here is a clear indication of this gradient inside of this material. If I had a uniform composition, this barium peak would be flat at the top with almost no tilt. And what we see is that we go from the upgraded structure, it tilts in one direction. We go to the downgraded structure, it tilts in the other direction in the system, and we can actually pull out what the real chemistries are. So we have real gradients inside of this material, and you can see the counter-indicated trends in the strontium peaks as well. Now, what's really cool about these is that we grow these things that have varying lattice parameters, and they remain coherently strained to the underlying substrate. So these are reciprocal space maps. We have the same in-plane lattice parameter, but a continuously varying out-of-plane lattice parameter in these structures, and we can grow both up and downgraded versions in this coherently strained fashion. You can also take a look at this thing. This is a Z-contrast image from STEM, and what you can see is as we go from the barium-rich to the version of the material we have more strontium, we can see the slight change in the contrast, but overall we have a nice uniform film. We don't see multiple layers of things. We don't see a lot of defects, and it kind of acts as a pretty model set of materials and films to probe how these compositional gradients impact the evolution of properties. All right, so the first thing that we'll start with was looking at just good old-fashioned hysteresis loops. And so if we start with the parent materials, here are the ferroelectric hysteresis loops at room temperature for barium titanate. Nice ferroelectric, centered loop, everything looks like we would expect. If we grow the single layer of barium strontium titanate, again, we're just above the transition temperature at room temperature. And we have this kind of nonlinear dielectric response, but it looks like a paraelectric material overall. So nothing too surprising. If you now take and look at the graded versions of these materials, it kind of looks like you took these two things and you know, produced some offspring of it, if you will, right? So we have something that's kind of halfway in between here. So we have a spontaneous polarization, but we also see the presence of shifts along the voltage axis in these materials. And this is coming from the presence of this strain gradient in the material. So you can take this shift and you can estimate a very rough value for an effective flexoelectric coefficient. And I would say take this with a grain of salt. But you know, we're coming in the ballpark of where we would expect for these sorts of materials. What we've realized over the years from looking at these sorts of things is that this isn't as simple as just bending a sample and putting a real true strain gradient. There's not only strain effects and flexoelectric behavior, but there's also chemical potential gradients and many other things. There are inhomogeneous charge distribution. All of these things are happening. So this is really a pretty complex effect in these compositionally graded materials, and there are many factors that are playing into this shifted hysteresis loop that you see. But overall, we see what we kind of expect for this behavior. All right, so what we found in these materials is that by putting in these compositional gradients, you can have very interesting temperature-dependent responses in these materials. And so if you take a look here at the dielectric permittivity and the loss tangent as a function of temperature in these materials, we can again start by looking at the parent phases. We see that there's a peak for the barium strontium titanate just below room temperature. There's a peak for the barium titanate near about 450 degrees, pretty much close to what we expected from the phenomenological models. Loss tangents go up dramatically as we get to the higher temperatures where the materials just become naturally more leaky, and also near the phase transition in the barium titanate. Now, what's interesting is if you look at one of the graded versions of this system, so if we put in the downgraded data, what we see now is we have this kind of broad, quasi-temperature independent response in these materials. So the kind of average dielectric response for this system is about 880 across this temperature regime. And more interestingly, the loss is greatly reduced in this material compared to, say, barium titanate by itself across this entire regime, even at very high temperatures, up to 500 C. So we have this almost quasi-temperature independent response. What about field dependence and tunability for these systems? So here is the dielectric permittivity as a function of applied bias, going up in temperature as you go down on the screen here. And so we can see relatively large tunability values even at relatively high temperatures in this system. We can kind of summarize this here. So we're in the regime of kind of 60 to 80 on percent tunability, all the way up from room temperature to like 200-300 degrees. And if you take a look at some of the kind of classic figures of merit for some of these devices, we see that we're above kind of the kind of standard cutoff, which is about 5,000 for kind of a 200 or 300 degree window, right? So we're really expanding the temperature stability of the large responses that can happen inside of these systems. So pretty interesting. Now, cool behavior, but we wanted to understand where these things were coming from. And to do this, we turned to Andrew Rapp and his group, and Ilya and various others to really help us dig deeply into what was going on inside of these systems. So the first thing I'll highlight here is some of the work that these guys did in creating an MD simulation for these compositionally graded structures. And this was quite a Herculean effort, but it ended up being very useful in the end. So what you're seeing here is a prediction for the, or a simulation for the evolution of the polarization as a function of depth inside of this material. So we're going from deep in the film towards the surface in one of these graded versions. And what we saw kind of surprisingly was that the MD predicted a large polarization gradient, a change of basically the entire polarization of the barium titanate as you go through the thickness of the film in this material. And what was more interesting was that when they simulated the dielectric response in these systems, they were able to very closely, the actual dots here are the experiment and the solid lines are the MD simulations, they were able to replicate the kind of trends that we saw overall. And the way we've kind of figured this out is by basically thinking of a bunch of individual layers of the different compositions inside of here. And if I go through at any one point, there's some layer of a specific composition which is kind of going through its transition temperature, and they're all just kind of shifted from each other. And so as we go across this regime, we're kind of adding the collective effects of all of these different compositional layers to give rise to this broad temperature response inside of these systems. All right, so this was kind of interesting. We didn't really expect to see a large polarization gradient in these materials, and so we wanted to kind of prove that this sort of thing was happening. It kind of goes in the face of what we'd expect from a textbook standpoint. And so we turned to atomic level imaging using transmission electron microscopy. So here we're looking at kind of the top fraction of one of these, across the whole thickness of one of these films. And if we zoom into the top portion of this film, we can get an atomic resolution image of the material. And we can begin to extract the local atomic displacements and get a local measurement for the polarization inside of these materials. And when we do that, so this is again graphed for this area near the surface where we have the largest change in polarization, we see a change in the local B site displacement from being relatively large at the bottom part to getting smaller as we go towards the surface. This ends up giving us a direct way to measure the strain gradient, which has ended up being on the order of about 10 to the 5 per meter. So a very large strain gradient in these systems. Now, if we zoom in here, we can extract what's going on. So we take the average of what's happening across here and take it as a function of depth. And I can graph the B site off-centering. Those are the red dots here. We see that as we go deeper into the sample, we have larger off-centering, so larger polarization, and it goes towards a smaller value as we get towards the surface. The purple data here is the same sort of information extracted from the MD simulation. It matches incredibly well. And the green data here are phenomenological models looking at what might happen using kind of standard off-the-shelf flexoelectric coefficients. Now, if we put the background dielectric constant to be something reasonable and what we would expect it to be on the order of like 8, we see that the system works to try to get rid of this polarization gradient. Even if you turn it up to 80, it doesn't really show much of a variation in polarization. But if you make the background dielectric constant infinity, which is pretty nonsensical, you can match up what's going on. This would suggest that the material is metallic or something like this. And in fact, it's better insulator than the individual materials were to start with. And so what we think is going on is that to take account for this large gradient in polarization or change in polarization, we have to have free charge that stabilizes. And this came up earlier in the discussions this morning. And if you just do a really quick back of the envelope calculation, to take advantage, to account for this gradient in polarization, we need a charge density of something on the order of 10 to the 19 per centimeter cubed. Now, that might seem like a large number of carriers for an insulator, but let me translate that into some other language that might make more sense. That's equivalent to having 0.05 atom percent control of the chemistry of one of these ferroelectrics. When we grow these films, if we can do 1% atom percent control in the films, we're doing very good. So there can be small changes in non-stoichiometry, creating defects, creating charges and carriers that could go into screening these sorts of things. And I think that's probably what's going on. Now, the interesting part is that even if we have this charge, it seems to be made immobile. These things are much more resistive than the parent materials. We have reduced losses and leakage overall, and so there seems to be a lot of things evolving with this electronic, with the carriers in these systems. Okay, so that's the first part of the talk. I want to shift gears here and give you another little vignette about another classic system, which is the PZT system, right? So we've all seen this many times, and we're all familiar with the phase diagram here. But what we're going to be talking about here are 100 nanometer thick versions of these materials. Again, we can grow the parent phases. We're going to pick something on the tetragonal side and something on the rhombohedral side of the phase diagram. We pick a substrate, in this case, again, gadolinium scandrate. We know the relative strains for the two parent layers. We can grow downgraded versions, and we can grow upgraded versions of these materials. All right, so we've been working on this for a number of years. Let me very quickly just tell you what happens when you make these. If you grow the rhombohedral version, you get a very complex domain structure here in PFM, and the films are typically relaxed. When we grow the tetragonal version, we get nice kind of classic CA domain structures. If we grow the compositionally graded versions, we get these very complex structures which look something like an A1, A2 mixture with lots of other things going on in the downgraded, but we get something that looks exactly like a CA domain structure in the upgraded structure. Now, this is a bit surprising because half the film is on the rhombohedral side of the phase diagram, and we wouldn't expect to see these sorts of things happening. Okay, so we can have these big effects overall and big strain gradients, and it can drive interesting evolution of structure and properties. All right, so what I want to walk you through to wrap up here is some band excitation switching spectroscopy data. In the essence of time, I'm not going to go through this whole process, but we can actually get spatially resolved pictures of the switching process inside of these materials. Okay. In here, I will show you what it looks like in cross-section in just a minute. So that's a great question. In fact, it does change as you go down in thickness. Okay, so we can take a look at the switching spectroscopy. If we do this for the parent 2080 PZT, we see very classic sorts of switching behavior that we would expect to see. We can see A domains running across the structure here. It kind of switches uniformly. We get symmetric switching response, textbook behavior. Now, if we do this for the compositionally graded versions, what you'll see is that these A domains are going to start to change in nature as we go to certain biases. We can effectively erase or apparently erase these A domains. So they seem to come back and forth, and there's some sort of memory about where they are. They always come back in the same place. So this is not what we expected. So in the tetragonal version, we can do the kind of stepwise switching. I'll just kind of bring this up here to make sure we get done to have some time for questions. We see very classic switching behavior. It nucleates fairly close to the A domains and then switches very rapidly in a very sharp switching process overall, and we can go back and forth in this system. So we have symmetric hysteresis loops. We switch first near the A domains, it proceeds sharply, and the A domains are essentially unimpacted by this switching process. Now, what happens in the compositionally graded version is a different story. So if we just think about how the domain structure should evolve as we go from compression to tension, we can change the expectation of these domain structures in this tetragonal version of a material, from having monodomain structures to sparse CA to dense CA structures. And so if we put this all in one film, we might think we have a dense structure at the bottom, sparse in the middle, and no need for these A domains at the top surface. So this was our kind of hypothesis for what the cross-section of these things might look like overall. So when we did cross-sectional TEM, you can just slightly see these domain structures showing up, these kind of needle-like domains that truncate in the thickness of the film. And I'll highlight those so you can see them better. So in these compositionally graded heterostructures, in fact, the structure does change as you go through the thickness of the film. This large strain gradient is creating these needle-like domain structures that truncate in the film. If we take this image, we can do a little bit more using something called 4D TEM, where we can extract the a convergent beam electron diffraction pattern to each pixel as we go through, and this enables us to map out the local strain profile inside of these materials. So here you're looking at a color map of the out-of-plane strain and the in-plane strain, so there's a big variation in the out-of-plane direction in the lattice parameter, but not so much in the in-plane. So it's kind of coherently strained with a changing out-of-plane lattice parameter. We can extract this strain gradient, again, on the order of about 10 to the 5 per meter. We can also extract things like the polarization, rotation, and there's these little bubbles of kind of high energy sorts of things happening near the tips here. All right, so we can walk through the switching process for this material. Things happen a little bit differently here. As we start to apply a bias, if we apply a positive bias in this system, we start to grow this A domain into this more classic structure. So we reinforce this A domain growing across the film. We switched the material at that point. Then as we start to go back in the opposite direction, we can push this A domain down. So it grows from this kind of equilibrium state, grows to the surface, then we can push it back down to this kind of reduced structure, and we see these A domains kind of go away. So you can kind of watch a cartoon movie of what's happening, so you can see the evolution of what we think is happening in the switching behavior of these compositionally graded versions of these materials. So if we go in the opposite polarization of bias, we'll see these domains get smaller as we go. So there's kind of like a springy response of what's going on. Okay, so the last thing I want to mention here is that this gives rise to different properties inside of these materials. So we're going to compare the tetragonal parent phase and the graded versions of systems. So if I look at a map of the coercive field across the surface, I can look at the negative coercive field and the positive coercive field. We see these things basically offset. They have symmetric switching. There's no built-in bias or anything. It's pretty classic. If I look at the same thing here for the compositionally graded version, I see that there is a presence of an offset near some of these domain boundaries, okay? And so it seems like there's some sort of restoring force. And we also see a macroscopically shifted loop. So what we think is happening is we start with this initial phase. As we apply a positive bias, we grow this domain across the structure. This increases the elastic energy because we're forcing this A domain in, but it reduces the electrostatic energy of having this domain that truncates in the film. And if we go in negative bias, we reduce this, and that increases both the elastic and electrostatic energy. And so essentially there's a restoring force. So when we remove the field, it kind of springs back to where it started in these structures. And this is consistent with what some people expected for these sorts of domain structures. Now, this also shows up as differences in macroscopic properties, like the piezo response. So here we see in classic CA that near the A domain boundaries, we have a reduced piezo response. But in this case, because we have these A domains, these ferroelastic domains going up and down, here we have enhanced piezoelectric response near the A domains inside of these structures. Okay, so I had one other example. I'm just going to leave you with a treat here of what happens when you put together weird structures together. And so what we did here was put together versions of material that have CA structure at the bottom and A1, A2 at the top. And we can actually get these kind of shark fin looking domain structures, which are C domains and CA structures mixed with A1, A2 versions of these materials. So we can talk about it more. They come up with crazy hierarchical structures overall. So with that, because I'm getting the hook from our chair, I'll just leave up these conclusions. So thank you for your attention, and I'll be happy to answer any questions.
Thanks a lot, Lane, for the very nice results and presentation. So we have time for questions. Please go ahead. Yeah.
About the first part, towards the end of the first part when you were talking about this compensation that allows for the polarization gradient. Now, if you reverse the polarization, then the compensation has the wrong sign, right?
Yes.
So does that mean it's not switchable? Or I'm confused because earlier you did show hysteresis loops. So.
Yeah, so it is switchable, but it's unstable, right? So what we can do is two things. So if you looked at the loops, they're completely shifted, right? So one of the polarization states is stable and one's not. So if I put it into the wrong configuration, it will come back. But if I heat it up and apply the bias in the other direction, I can flip the shift of the hysteresis loop. So we can rewrite that charge structure by giving it enough temperature and time and field to do these sorts of things.
What kind of temperature do you have to
A couple hundred degrees, doesn't have to be crazy. As long as we basically take it above the transition temperature. I mean, we don't have to go to like 1,000 degrees or anything, just above the transition temperature. I think that has a large part of it, large role to play.
This relates also to the first part of your talk. If you were able to measure TC along these graded regions, does it scale linearly with X, or what is happening locally? If you were able, I think you are not able to.
Yeah, so we aren't able, from the MD simulations, the best we can tell is it almost acts for some reason as if they're uninteracting layers, right? So it almost behaves like the strained version of that individual composition. So it absolutely scales directly with the composition of that layer and just kind of sweeps through space across the film.
But this is from MD, from your data?
From the data, that's what it looks like too. From the temperature dependence.
Linearly depending on composition.
Yeah.
That's interesting. Thank
you. Can I ask you your opinion about theoretical study of this project? Because you see, as I remember, we have about 3 different approaches. First was Pamir Alpay and Matisse, they do something, even book about, correct?
Yes.
No, they use gradient term, it's clear, it's absolutely strange.
Yeah.
Okay? Then we, Roitbert or somebody else, try to do something too.
Yeah.
Okay? What's your opinion? What is correct theoretical approach to solve this problem?
So we've tried a number of things too, and I think, yeah, right. And you can, so if you use the right combination of terms, you can even get a simple phenomenological GLD type model to work for these sorts of things. The MD did very well. It also the MD wants to spit out domain structures that don't show up because of depolarization and things like this. Yeah, so what we found is that kind of self-fulfilling after the fact, once we know what it looks like, we can go back and use the right terms in even a simple GLD approach, and we can get it to exactly replicate what we have. But beforehand, we didn't know what values of flexoelectric coefficient to use, what gradient energies, all these sorts of things to get it to work. So I think you can do it if you know these values well for your system. I just don't think we know them well all the time.
Okay, thanks a lot. We should move on.
Thanks.
Let's thank the speaker again. So the second talk will be given by Yakin Ivri